Please welcome to the stage Andrew Scobie, founder and CEO, the Faraday Grid.
Good morning, and thank you for having me in Calgary. I'm an Australian. I come from your future. And that's really not a good thing. In the last few years, the electricity grid in Australia has failed 5 times. As we have attempted to increase the amount of renewables in the system there, we've brought it to a point of complete instability. Australia once had, like Canada, a massive competitive advantage based on its cost of energy. Today, it has equal to the highest cost of electricity in the OECD. It has some of the least reliable energy supply in the developed world. And it has some of the largest levels of emissions. Clearly, things aren't working. And Australia isn't on its own. All around the world, the electricity system is failing us. We've done a fabulous job at focusing on generation, but we've yet to understand the implications for actually delivering to consumers. The electricity grid is not something we should treat lightly. Over the last 137 years during its lifetime, it's lifted billions from poverty, grinding poverty. So perhaps we can take a moment to think about Grid 1.0 before we start to give consideration to Grid 2.0. Grid 1.0 didn't magically appear out of nowhere. In fact, Grid 1.0 was an expression of the values of the people of its time. I today live in Edinburgh in Scotland, in the home of the Scottish Enlightenment. Adam Smith, David Hume, lived in the face of the last great clash between absolute monarchy and rational modernity. And in that moment, they sparked, the Enlightenment generally sparked, and his scientific inquiry as to how we could harness the natural world to pursue human ambition. And out of that scientific inquiry, the likes of Michael Faraday, moving through to James Clerk Maxwell, who mathematized his work, and on to William Stanley, the inventor of the transformer, we radically transformed the world. The grid and the energy system was there to manifest the needs, desires, ambitions, and hope of generations past. And before we start to give consideration to what our electricity system should be like as it attempts to meet the needs of the future, perhaps it's worth reflecting on how and what that actually was, and not throw the baby out with the bathwater, not to let go of what was one of the principal drivers of our prosperity, health, well-being. And yet I'm absolutely a believer in decarbonisation. It's a necessity and it is a fundamental value of our times. That grid forms the nervous system of our very economy, of our very society. And if we treat it without respect, we end up with very considerable problems. Both the government of the United Kingdom and of Australia have made it very clear that within 3 days of the energy system failing, social order breaks down. It's not something that we need to be treating lightly. But nonetheless, that system, that grid, is in fact not working any longer for us. It's not meeting our needs and requirements. We challenge it every day with ever-increasing amounts of renewable energy, with distributed, variable and volatile demand. Electric vehicles, all of the digital devices in our homes are introducing into a system a fundamental challenge that the grid itself was not designed for. The grid itself formed part of an energy system which had at its centre large, principally coal-fired power stations. Those coal-fired power stations provided a bundle of services. They didn't just provide electrons, they provided balancing services as well. The inertia that came from the spinning turbines, that mass levelized and balanced the signal throughout the system. So what we have is this centralized system based on large generators with a grid which is no more than a transportation system out to consumers at its edge. That grid is fragile, that grid is passive, and that grid is rigid in its nature, and utterly unsuited to the challenges of our day. As we continue to increase, as Michael made clear earlier, the amount of renewable energy that we're going to put into the system, the ever-increasing amount of electric vehicles, and the heat load that we're going to put onto that system, the system itself is completely not designed to carry that function out. We need to reconceive of that energy system. And that energy system needs to be meeting our needs in our time and to be limitless in terms of its capacity to meet our requirements for the future. If we have any hope or ambition to meet that outcome. We talked earlier about the massively reducing cost of generation. But the massively reducing cost of generation is fairly insignificant, right? We talk about levelized cost of energy, but levelized cost of what? Of electrons without balancing services? Digitally injected into a system without providing the stability which allows us to get to consumers? What actually matters is the cost of energy to consumers. We have to deliver energy to consumers reliably, cheaply, and to be clean, right? But as it is at the moment, we can see a crash in the cost of electricity generation. Yeah, but generation represents no more than 10% of the cost of energy to consumers. So statistically, if I drive down the cost of generation, but I massively drive up the cost of transportation and balancing services, all I've done is destroy our prosperity. All I've done is reduce our options for the future. That isn't something we should be taking lightly. It isn't just this binary decision between carbon-based generation on the one hand and nice clean energy on the other. That would put us into a position where we were making a trade-off between human welfare and our environmental concerns. And that trade-off just isn't necessary. We're now quite able to have an energy system which doesn't require those trade-offs anymore. This is not a dream. This is not a hope. This is actually an actively available choice for us today, and I'll come back to that in a moment. So, 137 years ago, William Stanley invented that key articulating technology, which was the transformer, and it transformed literally our entire society, our future, hopes, dreams, ambitions, what was possible today. I think Michael spoke earlier about mobile phones. Well, mobile phones simply wouldn't have existed if we didn't have the enabling capacity, the prosperity that's driven those kinds of things, yes? We need to have a system which is capable of supporting all of our choices and delivering on our future needs for our children and our grandchildren. So we have a system which has not changed in 137 years. There has been no fundamental disruption, innovation, in 137 years within the grid. We are asking this system, which was just a form of transportation, a highly efficient, highly fragile, needing to operate within minus 1% of its optimum at all times, system, we're asking it to suddenly support an entirely distributed society with distributed generation and distributed consumption. It wasn't designed for it. It just wasn't simply designed for it. So for us to myopically focus on either supply and demand would be utterly ridiculous, frankly. Yeah? We have to have a way in which we can balance supply and demand in a manner which we can all afford to carry out. So you have a situation around the world today in which there's ever-increasing numbers of people defecting from the system. You hear it all the time, grid defection. So people are either partially or fully defecting from the system. So who can defect from that system? Middle-class people, upper-class people can defect from that system. But if I take the lovely big bell curve of distribution of all of the revenues associated with that system in terms of the marketplace, and I take the center out of there, if we all defect out of the middle, who's going to be left on that grid? Who's going to be dependent on that grid? Two sets of parties. One, the makers, industry. Industry who need a grid, who need cheap, reliable energy to continue to produce, whether you're in the services business or whether you're in Trump's 19th century world, all of that, right? All of that, no laughing. No political speeches. All of that, simply placed, they cannot live without that system, yeah? So I take the middle class out of the middle and the upper class out of the middle, and over here on the left-hand side, I've got poor people. I've got the less well-off. I've got the more marginal in society who also can't afford to defect from the system. They're not able to afford California's $15,000 in the cost of solar panels, which will be mandated for rooftops from here on in, right? They can't do that. It's not going to happen. And we as a society simply don't have the economic capacity to do so. And if in the intervening period we continue to increase the cost of energy to a point at which we can't afford it, right? How are we going to, where's our capacity to support these people over here going off grid? So we don't go off grid, right? Whether we want it or not, we have a grid, yeah? We have a grid. So now it's a matter of whether we've got a good grid or a bad grid, yeah? So then, there we are, we've got grid 1.0, which gave us every single person in the room is actually made up of the byproduct of the grid distributing that, right? Everything you eat, every house you live in, all of it is actually a product of that system. Before we walk away from that, we should be really, really careful about what that means, yeah? So Grid 2.0, I've been asked to speak about Grid 2.0, but Grid 2.0 is largely speaking just Grid 1.0. Right? With a whole lot of add-ons, with extra layers of complication and sophistication as we seek to ameliorate the system, right? We've got this incredible problem of dramatically reducing centralized generation with all the inertial contribution to the system, and on the other side, we've got a radical increase, according to Michael, of the amount of asynchronous generation which provides zero balancing services to the system. Right? So I have a multiplier of reduction, multiplier of increase, and what I get is a geometric curve of instability. And every single grid in the world, whether you're Norway or Australia or the United Kingdom or France, you name it, you're on that curve somewhere. It's just a matter of how far you go down it. So when you start off introducing as a nice solar developer somewhere, you start off sticking amounts of renewable energy onto that system. The first percentage point, second percentage point, everything's tickety-boo, right? And then you hit an inflection point and things stop being tickety-boo in a real hurry. And because the grid was built out without us actually understanding it, we didn't design the grid in any sort of really meaningful sense. It was an additive process, right? So as we've added to it, we've got absolutely no comprehension of how, at what point you fail. All we know, every ISO in the world pretty much knows that they're getting close to that point without knowing where that point is. So in the United Kingdom, every year in summer and winter with all those peaks, the system operator comes out and says, this year we expect the grid to crash, right? This year we expect the grid to crash. This summer we expect it to crash. It's going to crash, right? So we therefore are chasing our tails endlessly, either adding enormous expense of storage to that system, or we're adding smart grids to that system, et cetera, as we attempt to actually achieve the impossible, yeah? Because if you have a centrally controlled system with an ever-reducing center, but I'm attempting to continue to centrally control it, and unlike the rice transportation business, rice moves at the speed of ships and trucks, right? And then I want to control that, and I pick the phone up, and my telecommunications operates at the speed of light, pretty much. I can control that system pretty well, right? But what do we know about the grid, right? The grid operates at effectively the speed of light. My ability to communicate out and control that system, control demand and get it back again in any meaningful sense, this is ridiculous. This is a hiding to nowhere, yeah? So what can we do about that? On the one hand, we can either keep stacking things on top of it and call it Grid 2.0, or we can actually more fundamentally rethink the entire energy system and ask, what are we seeking to achieve here? And we can look to the precedents, not of the 19th century's greatest engineering feat, not of the largest machine that humans ever built, not as the provider of all our health and prosperity, but you can look to the 20th century, and we can look to the greatest machine of the 20th century. The greatest machine of the 20th century is the internet. And the internet, when was the last time the internet failed? It doesn't fail. It was designed not to fail. And it's designed not to fail because it's not centrally controlled. Yeah? The internet is a decentralized control ontology. We have routers distributed throughout the system who simply manage their localized area. And they provide us with a stable information system which is able to deal with decentralized generation of information and decentralized consumption of information. Because with the internet, as dispersed as it is, it's the center of all of that information system. Yeah? So I would suggest to you, instead of attempting to convert a 1920s car and hot rodding the thing and attempt to make that actually meet the needs of our future, we'd be a whole lot better off looking to how it is that we can convert our energy system to one which is essentially based on decentralization of both generation and consumption. You shift the locus of control to the grid itself. And that's not a dream. We launched that in 2017. That's the Faraday Grid. And the Faraday Grid is a system of decentralized control in which we replace, principally in the location of the transformer, stat-vars, stat-coms, inverters, converters, rectifiers, capacitor banks, and transformers, with a device which is called the Faraday Exchanger. And the Faraday Exchanger dynamically balances voltage, frequency, harmonics. It removes all harmonics. It maintains power factor at unity at all times. And it balances phase, right? And it does that in an entirely distributed manner. And now all of a sudden, rather than having a one-way, highly fragile system, we all of a sudden have a system which actually is anti-fragile in its nature, which benefits from volatility, which has a capacity to more than double the amount of renewable energy in the system and simultaneously reduce the cost of energy to consumers. How does it reduce the cost of energy to consumers? If I can increase the carrying capacity of the grid for volatile energy because I can take an unstable supply in and I can provide a perfect signal out the other side at all times, it allows me to massively increase that carrying capacity in a manner which is just quite extraordinary. But what you have at the generation side of things is an old-fashioned coal-fired power station, nuclear power station, any of those beautiful things, right? They all had a marginal unit cost of production of about the same as the first unit of production. But if instead I look at renewables, what's the fabulous, extraordinary thing about renewables? It's got a marginal cost of 0, right? The first unit of production is effectively your capital cost, and the curve does this, right? And over here in my marginal unit of cost of production, it's so close to 0 as not to matter, right? But the problem with it at the moment is I can't integrate that last lot of energy into the system. It's being curtailed off. It's being curtailed off because the grid itself can't accept that energy. So the last about 12% of energy can't be injected into the grid, right? And you imagine a world in which we can more than double the amount of renewable energy being injected into the grid, and 100% of that renewable energy can be injected into the system. Now we're talking about massively reducing the cost of energy to consumers, because we haven't affected just the gen end of the equation, we've affected the totality of the value stack all the way through to the consumer. Right? So now I've got an energy system that could go anywhere to anywhere, agnostic to supply and demand. Yeah? As opposed to a fragile one which is incapable of operating outside in any meaningful sense outside of plus minus 1% before it becomes unstable. That plus minus 1% really matters, guys, because what it means is that historically the whole system is volumetrically balanced. Consumers change their behavior out here and the system operators got no choice. They have to buy big chunks of energy and they're buying it without regard to the cost. And as we increase the instability of the system, as we inject more renewables into it, that task gets harder and harder. And therefore, they're having to buy more and more of that really high-cost marginal units of production to put into the system to maintain system stability. We're on a hiding to hell in terms of delivering stable, cheap energy within Grid 2.0, for the reasons I explained earlier, or the existing grid system. But if I've now got an agnostic system, agnostic to supply and demand, I'm being told to wrap it up, so I'll wrap now, right? So if I've got an agnostic system, I can now start to allow consumers to balance supply and demand across the system in real time. I'll bring it to a conclusion there. I thank you so very much for your time, and I look forward to the rest of the event. It's fabulous. These guys have a great thing on. Thank you.